So I don't want to show student data, but I can go to a roster, I can click on their thing, and I can see exactly what you did. So again, you can email me, and I'm probably will be able to find out what's going on. So let's just go through. All right, that's an op-amp, op-amp. Okay. How late can you guys stay today? 1:30? Okay, well, I mean, without anybody asking a question, it's really hard just to talk to yourself, so. Okay. So this happens to be a current to voltage converter. All right. And actually, just kind of show you something interesting is like where maybe you might ask, where does he get these circuits? Is he just trying to be a pill or something? Anyway, if you go into LT Spice, I'm going to pick one of their older parts, right? You can actually get a test jig, right click it, go to their website. Oops. You can get free samples. And you can read the data sheet. Now, I'm not going to go all in. I'm just going to just show you this one cool thing about data sheets at the end is that they want to sell you their op-amp. So they're going to show you how to use it, all the cool things you can do with op-amps. That's what's on the inside. So here's what are called application notes. And so right here, this is a photodiode amplifier. And in fact, I had kind of done this problem last time. All right. And yeah, we have a capacitor here because we're getting rid of noise and we can get more gain by having two of these resistors here. And there's some other benefits of doing it like this. But this is a photodiode. Light comes in and creates current. And just looking at this circuit, it's an op-amp, it's always good to start assuming an ideal op-amp. So the open loop gain is infinity. I see a resistor and a capacitor connecting the output to the negative input. So there's negative feedback. So that, combined with the fact that an ideal op-amp has an infinite input resistance, so the currents in here are zero. So given those three things, I know that node 2 and 3 are very, very close to each other. And so we say that they're actually equal to each other. Now, what that does is I have a diode, the light comes in and it creates current, but the voltage doesn't matter because it's being forced to be zero voltage drop. And so you get this linear relationship. The more light, the more current. But it wouldn't be nonlinear if the voltage were allowed to change. This whole op-amp just fixes this at zero. That current flows. Actually, it's flowing. Yeah, it's flowing this way. The current flows. There's a voltage drop here. There's a voltage drop there. And then you sum these voltage drops, and that gives you V out. All right, so this is just a simplification of that. And yeah, why do I explain why and where it comes from? Because I feel that when you know what it's supposed to do, it's a little easier to remember what's going on. But from like an analysis perspective, it's kind of interesting too, because there's a little bit of a trick question. And what I'm going to do is just put down below an inverting amplifier. So we have R. Here we have a current source, right? Here we have a voltage source and a resistor. Well, when we do our nodal analysis, we set up our currents. If that's R1 and R2, we get IR1 equals IR2 because I minus equals 0. Right? Then, well, what are these two? Oh, well, V in minus Vx R1, Vx minus V out divided by R2. And then you go from there and you can prove that Vx, because these two nodes are equal or very close, Vx is equal to 0, and then you can just solve for, V out equals minus R2, R1, V in. That's like the straight, classical problem. This, it's actually the same thing. But it can give you a little bit of trouble because, in fact, it's simpler. So I have IS, right? That's going in. And then I have IR, right, coming out. Oh, wonderful. I'm going to call this node Vx. All right. So then you write, now you use Ohm's law. And so I'd say, oh, Vx minus V out divided by R. And then you're like, well, wait, here's my IS. Well, where's my V in minus Vx R1? You don't need it because it's a current source. It's right there. There's nothing to do. Now, when I'm doing these problems, I'll say, oh, it's ideal. What does that mean? Open loop gain equals infinity. That means Rn equals infinity. Notice negative feedback. Conclusion, V plus equals V minus equals Vx equals, in this case, 0. Because we've defined it that way. So now sure, I can use V out equals the open loop gain, V plus minus V minus. And in this case, V plus is 0. In this case, it's Vx. Put it in for V out, solve for Vx, substitute it, and let the gain go to infinity and prove the same thing, right? But really, this is infinite, that's infinite, negative feedback, these are equal. And in this case, Vx equals 0. So now, all that remains, right, Is equals Vx is 0 minus V out over R1, solve for V out, and that's not R1, it was just R. Sorry. All right. It takes a current, multiplies it by a resistance. So you can take a microamp, something tiny, and multiply it by a mega ohm and get something big. Now this kind of circuit, right, you can have your detector right on a robot. I know, I can't draw very well, right? And when there's more light, when less light is bounced back because this is dark, the voltage goes down. When it leaves the line, more light comes in, and so the voltage gets, well, actually more negative in this particular example. So even though this robot might use a microcontroller to control it, how do you get the signal into that microcontroller? And you say, oh, well, microcontrollers have A to Ds. Sure. But how do we convert light into a voltage that the A to D can use? That particular circuit. Okay? Where's... All right, here's another interesting example. So when I look at a circuit, I try to think, what can I recognize first? And I look at this, and hey, that's a voltage buffer. Sure, I know that when I draw them, I tend to draw them that way, but the negative feedback is coming down instead of going over the top. But yeah, that's a voltage buffer. So whatever voltage is here is going to be here. So I'll just call that Vx and V naught. So to me, just for looking at it, V out equals Vx. Now, it can happen. You're on an exam. Maybe you had something kind of memorized because you used it so much, but then you might forget. So let's just go over a quick analysis of the buffer. And there's more than one way to do it. So one way is it's ideal. All right. That means the open loop gain is infinity. Rn is infinity. Notice negative feedback. Right? So one thing is V plus equals V minus. So V plus right here equals Vn. And because of the negative feedback and the open loop gain and there's no voltage drop, these two things are equal to each other. But notice, I'm calling this V minus, but follow the wire. It's also connected to V out. That's it. That might be the easiest way. The thing is there is no nodal analysis, right? Because this is a voltage source, this is a behavior voltage source, and there's really no potential drops to write currents, okay? What sometimes people do is to kind of show where it comes from. You use whatever analysis technique you need, but V out equals 1 plus R2 over R1, Vn. Now, R2, it's a wire, right? R2 equals 0. R1, well, what's in between here? Nothing. So it's actually infinite. Or very, very big. All right, well, let's substitute that. V out equals 1 plus 0 divided by infinity. Vn equals Vn, right? So even if, yeah, I mean, I was helping my son with his math, and there was something about complete the square. I had totally forgotten it. Because it's like some weird Common Core thing that turns out there's such an easy equation, and drawing the picture takes 5 times as long. But anyway, like I had kind of had to look it up, but then it comes back right away. And so this could happen to you. Like when I'm designing circuits or thinking about things, I look at that as a buffer, and then I go on, or essentially, yeah, I might, go on with my life, right? But for instance, you look at this circuit and you're like, oh my God, what's going on there? Right? Well, I would just look at it and say, ideal op amp, there's, even though there's a diode, there does seem to be a path from out to in, from out to in. And so these two nodes are going to be equal. Oh, well, that makes it a lot easier because now this node is at 0, right? Then I would look here and say, well, you know, hey, if this is an input, I can do superposition. I'll tie this to 0. Hey, that's an inverting amplifier. Oh, now what about this input? Oh, I'll use superposition. Short this. Hey, it's a non-inverting amplifier. Add them together. So that's how you would puzzle it out. But what if you would what I guess what I'm saying is, you know, there's days where you can forget something like what a non-inverting, not by the time you graduate, you won't forget it, but as we're learning it, it's possible. So what I was trying to show you here is, yeah, myself, this is embedded into my neurons until I don't know when, right? Which might not help you if you haven't used it enough to where you can't forget it, right? Like when you graduate. So I just tried to show you 2 ways of rederiving it that'll get you back on track. So just like I was helping my son, I had some ways of like, oh, okay, working it out from basic principles quickly so that then I could do whatever it was they wanted to do. So right now, V out equals Vx. I need my relationship that I equals 0. So I have IS, I have IR, there's one node, all of IS goes into IR, right? Because no current flows. IS, well, that is the input. And in nodal analysis, inputs really are currents. Even if it's a voltage, we convert it to current. You might not realize it as we're doing it. All right, so what's IR? Plus, minus. That's Vx. What's ground? 0 divided by R. IS. Solve for Vx. IS. R. Well, from our buffer, right? Oh, well, V out equals Vx equals I source R. So the cool thing about this problem from like a teaching perspective is that it tests whether you get that this is a non-inverting amplifier. It tests that you know no current flows in here. And then in a more complex way, like, do you know V equals IR? Right? Because we have current, right? So what is voltage? Current times resistance, which, yeah, we called it nodal analysis, but that's all we were looking for, right? Okay, so the question was, could you use source transformation? Oh boy. No. Now you're catching me. So source transformation. So the voltage is going to be this times R, right? IS times R. So it's a voltage because there's a plus minus. The R is now in series, right? Which which is a real problem. It's not going to work. This analysis isn't going to work because the current here is 0, unless I've screwed it up. Oh, let me figure. What I thought was you had a voltage and a current, a voltage and a resistance, which then you could convert to a current and a voltage. I thought that was the back and forth. Because there's the Norton, right? Because this could be Thevenin, this would be the Thevenin, this would be the Norton, right? Unfortunately, well, and again, I might have to look it up, but when I do that source transformation and then put it in here, the ideal op amp now says it's 0, so it doesn't work. And there are times where those source transformations don't work. And I thought I had a few examples in R98 where, yeah, it doesn't work. All right. But I can look into that. Anything else on that? Okay. Okay, so that's the inverting. We did that last time. So this is an interesting problem. Even though you should have the answer memorized. So you get used to drawing things a certain way, right? And yeah, I have my favorite way of doing it, right? Here's an inverting, then here's a non-inverting, right? But, what if I drew it like this? Would that throw you? Would it throw me? Well, sometimes the things with circuits are, it's so graphical that when you could draw it backwards and it might seem totally unrecognizable. So even though it's something that you do know, sometimes professors like to just draw it a funny way just to see if you're paying attention. That's not necessarily the intention of this question. That just could have been, whoever wrote that question, that could have just been the way they like to draw circuits. Because in 110, you do system flow diagrams, and you have a summer, you have some transfer function, another transfer function, and you subtract it. And so you have a transfer function, you have out, it gets modified and subtracted from in. Well, op amps are like that. And so here's the plus, here's the plus, here's the minus, here's the minus. This GS is just voltage division, and this HS can be a variety of things. All right. So it could be that's just the way they liked it. Now, I tend to draw my circuits this way and the signal flow diagrams this way. I don't know. Seems better to me. So let's assume we can't, we don't recognize this circuit for what it is. I'm going to put some current directions and some voltage drops. I'm going to say that it's ideal. That means open loop gain, infinity, R, infinity, R2 gives negative feedback, right? Thus, V plus equals V minus equals Vx equals Vn. So actually, Vn is right here, which will make it a little bit easier. So now that's an input. That's an output behavioral source. So really, there's one node that is unknown. That means one. We need to write one nodal equation. IR2 equals IR1, IR2, V out minus Vx, R2 equals Vx, whoops, minus 0, right, because it's at ground, R1. Vx equals Vn, so substitute. V out minus Vn, R2 equals Vn divided by R1. So let's, combine terms. Non-inverting amplifier. Maybe you saw that, right? You probably did. I was just pretending you didn't see it. Okay. Now the problem it gives you the current directions, and if you don't use the current directions provided, you might get the backwards answer. So here is, we have an op-amp, and the question is, I out equals what? And we have a load. And you might think that's really going to change things, but op-amp is ideal. It's also is a ideal behavior voltage source, right? So whatever V out is, this can supply infinite current. Sure, there's a node here, and you might think, oh, I got to do a nodal analysis here, and now I have to do a nodal analysis here. But you don't really. V out is something times the difference here. So there's really only one node that you don't know, right? Because you already know what V in is, you know what ground is, and in a sense, you know what V out is because it follows what's going on here at node Vx. So in fact, R3 doesn't affect V out. You don't have to do a nodal analysis for it. So where would I begin? Well, I just kind of notice, well, what did I have before I added R3? Hey, this is inverting amplifier, right? Because this R3 isn't going to change what's going on here if it's ideal. So then all I have to do is write V out equals minus R2, R1, Vn. So now I know this. I don't really need to solve for a nodal equation here. But and if I was asking you what the current through here is, oh, it'd be whatever V out is divided by R3, right? If you wanted to know what this is, right, I've got it pointed in the opposite direction, but you could just do it. So in fact, but we're talking about I out coming out of the op-amp. So I out is coming into that node, right? What else is coming in? IR2. Where is it all heading? IR3. Now, I out is the thing that we want. So we just have to do this. Okay. IR3. That's the current direction plus minus. That equals V out minus 0 R3. What is V out? Minus R2, R1, Vn. So that's easy to calculate. IR2. Well, that was the current definition, so I have to use it. So that's plus minus. So that's Vx minus V out divided by R2. Now, as we've shown, Vx equals 0. right? Because it's an ideal op amp, it's in the inverting configuration. So really, IR2 equals minus V out over R2. All right, so now we come over here. I naught equals minus R2. This is R2, so minus times a minus is just is R2. What is IR3? That is V out divided by R3. All right, what is V out? Oh, minus R2 over 1 V in, right? There you go. This is really critical in testing. Yeah, it tests whether you can recognize quickly that this is an inverting op amp, right? And that V out is minus R2 divided by R1 times V in. And then it tests whether you can set up the nodal analysis equation right. So yeah, I've defined the current going this way. I defined this current going that way, and I defined this current going that way. So IR2 is coming in. I out is coming into the node. IR3 is coming out. Then it tests whether you do the voltage drops right. So IR2, Vx minus V out, because it's plus minus Vx minus V out. IR3 is V out minus 0 divided by R3, because that's the current direction that we've selected, plus, minus. All right. And yeah, knowing that an ideal op amp can supply current to any resistor. In practicality, the limit is 40 milliamps. Now let's just do some planning. This is almost the same problem, except it's in a non-inverting, and that it just looks funny. That's the chain, two non-invertings times each other. So we've kind of done that. That's two invertings times each other. Two inverting times each other. We got this problem a lot. Oh, two non-invertings times each other. Same. No, wait. An inverting times a non-inverting. Here, we've done this problem, except the current was over here and was facing up, right? Practically the same problem. Oh, and then what do we have? Equivalent resistance? No, that's not, you guys know that. This one, yeah, it's tricky. So I think next time we're going to go over op amps again. We're going to continue. Then I think it's, yeah, probably those complex things, because most people did really well on the math and the RMS, and then maybe we can just start quizzing ourselves, right? But maybe, yeah, that's the formal lecture bit. Any questions? Okay, let's see. Nope, nobody else came. That's okay. All right, guys. See you next week.